Hello, everybody. Today, let me quickly walk through this paper published on mechanical systems and signal processing. So the title of this paper is Bearing for Diagnosis Based on Wavelet Transform and Fuzzy Inference. So I'm the author, one of the authors, Shensheng Lo, and Kenneth Loparo was my advisor at Case Western Reserve University. So we published a paper 2004. I submitted 2003. So so this is abstract. Though this actually we say we deal with a new scheme for diagnosis of localized defects in a bearing based on two techniques. One is wavelet transform, and the other one neurophysical classification. So basically, this is looking at the bearing system. Here's the test bed. So there's the induction motor, and we mount the accelerometer on the housing, and there's a data acquisition system connected to that to get the digitize the signal. And this one on the shelf, we can apply different load. So this is the test bed used for collecting data. And what we're looking at is the bearing. So we put normal bearing and bearing with inertial force. The force was created arbitrarily. So in this case, the force is 40 mils by diameter, and the depth is 40 meter, is a pretty big one. So we have applied the same size force to the inner race, out race. So we collected four groups of data: normal conditions, inner race force, bulk force, and out race force. So and also we apply different load conditions, say no load, zero load, one level node, two level nodes, and three level nodes. It's actually 1 horsepower, 2 horsepower, and 3 horsepower. So when we get the data, we process it. First, we normalize that signal. So normalize is using standard to normalize the formula. Is SI minus mu is the mean and divided by standard deviation. So standard way of normalizing data to 0, 1. So and to check also want to check if the signal is normal distribution. So we use this statistics analysis that we say test a good fit. So and with a normal data is like this. It's pretty close to normal distribution, and the inner race is close too. But we look at this ball for the shape already changed. It's pretty thin. It's thinner than normal and inner race force. We did not plot the outer race force because in the paper it is said the outer race force data was corrupted, so we did not use it for this analysis. And so we check all the normal distributions. So and we just draw the conclusion that the normal for inner force more consistent with normal distribution, and this one is less fit to a normal distribution. And also we can check the data very quickly by applying high order statistics analysis, like what we put here, like the skewness analysis. The third skewness represents the third order of statistics. You can skew that way or skew that way. So, but in this case, this data is not skewed, so it's symmetric. And we look at the kurtosis. So here is obviously it's thinner than normal distribution, and this one is fatter than normal distribution. So in this case, if it is thinner, we say longer, the tail is fatter, or distribution is shorter than the tail is thinner than kurtosis than the 3. So we can calculate the kurtosis and look at the histogram, we can tell how far this set of data is away uh, from uh, uh, from the standard normal distribution. So this just introduced says skewness kurtosis. So we did not use that in this paper, but I want to mention that for easy check. But this one I used two techniques already. Histogram, visually inspect the histogram. We find this is thinner, and if you calculate the skewness, you calculate kurtosis, you can tell the same thing. And this is good. This is a statistical test of goodness of fit. That's another way to test that. So, uh, um, and you can look at this. So the criteria is those with p-values larger than 0.5 are considered to be represented to some degree by normal probability distribution. So look at this p-value is 0.7, pretty high. It's 0.05. This 0.05 is, but without the load of 0 horsepower load. But when you apply load, this value drop very quickly for both for. And this one maintained a high value, and this 1.1 high value. This dropped when you apply the 3 horsepower, but still higher than 0.5. So this safely be considered as normal distribution, but this one is already far below this reference number. So this is consistent with our visual inspection on the histogram. So okay, that's just the normal distribution check. So then this part of the paper is for completeness of the paper, we put the wavelength analysis. This is theory. So what is the wavelet analysis? You can look at check online, Google or encyclopedia, and and here is a different way of doing signal analysis than Fourier transform. Fourier transform is convert the time series signal into time domain signal into the frequency domain, and you lose the information in the time domain. But by applying wavelet analysis, you transfer that from time domain to time frequency domain, or if you use discrete wavelet analysis is transfer that from time domain to time scale domain. So you maintain both time and frequency domain information when you transform that. So and also the another difference is the Fourier transform. When you do Fourier transform, you use a sine basis, sine and cosine basis, and when you use wavelet transform, the basis is wavelet, and wavelet need to meet in order to design the wavelet basis, you need to meet a certain mathematical requirement. That's something you're gonna look at into the book. I'll look at some YouTube video. So I will skip this. But in general, when you do here is show if you do a wavelet transform, the signal will be decomposed into approximation implies different levels, say n level or 5 levels of details. A level is like the signal pass through a low pass filter, and the rest of what we call details from are actually this like the signal is filtered with different band of a spectrum. So and here's the example. So when you have the normal data, apply 0 horsepower load or 3 horsepower load, and we can see that for this, obviously there's an increase in this detail. So for this is pretty similar. This is similar level, similar. This is a little bit thinner, but this one is always bigger. So the change of a load can be reflected in detail 3 in this spectral band. So this is a test, and you can tell even the frequency band by doing this. So and also. We look at this. So this normal versus inner rest force. So we decompose into approximation and the 5 level details. You can see, this signal you cannot see anything, right? It's the probably on the same scale. But this one, you look at approximation, this is much smaller than this. So it means you can use this as a feature. And this one is a similar level, but D4 is a big contrast on the scale. And same for D3. And the D2 and D1 basically they maintain the same level. So what we can see is to um, the components D3, D4, and Fi basically can help us separate normal from inner reservoirs. So, and then let's compare normal with the ball for you can see this is in a big contrast. So this one is big and this is small, big, small, big, small, big, small. So A5, D5, D4, D3 can be used as the features for separating normal and the ball forward. So and then we can say safely based on that the inspection we can select uh, the 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 details and the approximation A and the D. So and the form the vector. I mean, actually easy. So you can use all of them. So to form the feature, and then this is just because we know what is for what is normal. We just calculate using the Euclidean distance method and the correlation coefficient method and see how we can separate. So say this is a compare normal condition with normal condition. And it's distance zero. So it means the center of the cluster. If you got two class of data, and one is the trend data, the other test data. So now it's a zero. So now this why is a zero because you use the same mounted same group of data. So it's zero and correction is one. And then and here is the inner rest. You can test when you do the inner rest. So the second is zero. The distance is zero means that overlap the center of the two data set overlap. It's the same data set actually, and then this one correction is one. So and this one is close to zero. So is round to zero. Is not absolute zero, and the decision making process. So then what we already taught used. So Euclidean vector distance, and then there's vector correlation coefficients, and there's Euclidean distance is defined as you have two sets of data, and one is here, the other I'll put it here. So one you have a data, one center is here, the other one is here, and you calculate the distance of the two clusters. So that's how you do that. And the conventionalist is basically you do statistical calculation. So you have two vectors, you just do covariance of two vectors and divide it by standard deviation of both. So it's still a statistical check of how they are related to each other. So here you can see, oh, when I test the normal using test sets, different sets of test data, this is really 0.029. This is 0.957, and this one is V2 is inner restful for and you can tell this is much smaller than the other one, and this one correction is close to one, and this one I forgot to say it should be put black font, but this one is 0.99 is close to 1. Correction is highly corrected, and the distance is short. So this is this two method, and then we introduce the third methods. I mean, in this one we don't have big data set, but potentially we may have big data set. So we evaluate different classification methods, like this one as we call ENFIS. ENFIS basically is a neural network using fuzzy functions, fuzzy logic in it. So if you look at the MATLAB toolbox, it's not in the neural network toolbox, machine learning toolbox. It is in the toolbox of fuzzy logic. So this is when I walk through. So it's a quick way to learn this is just walk through the toolbox for MATLAB, so and then run through that. So then you know all the functions and how that works. But to understand theory, you need to read the textbook. So this is the structure of ANFIS. So if you want to learn more, just try to find a book or find a YouTube video. So and then fuzzy logic is a good thing because why do we use the ANFIS? The good thing is we put the fuzzy rulers and membership functions. And the neural network has a drawback in that you cannot interpret the inference or prediction when you use the trained model for diagnosis. But potentially with the rulers, we may dig into look at the membership functions or how inference and give interpretation. But in this paper, we did not get to that deep side. We just use it as a classifier. So I just skip that. So this is how you define the membership function. And this is basically defined as linear. This is like defined as nonlinear function. And then you train it. So this data set is not too complicated. But if you have more data, like you do a lot of tests, the combinations are big, and then this method can provide you more advantage than the simple methods the two simple methods we mentioned before. One is the Euclidean method. The other one is the what is that? The other one is the statistic correction coefficient calculation. So this is ANSYS. So the wavelet we use is called DB. Is Dobitsch's. Professor Ingrid Dobitsch is a distinguished professor of mathematics, electrical and computer engineering (ECE) at Duke. Duke is Harvard, as we call it, Harvard in Southern America. It's not South America, in the southern part of the U.S. So look at the owner award is the National Academy of Engineering, is a fellow of Mathematical Society, is a fellow of IEEE, is a member of say National Academy of Science, get award, and then is also a member of I think is also a member of National Academy of Science. So is here. So like elected member National Science Academy 2013 and 2015 was elected into National Academy of Engineering to honor his contribution to the theory of wavelet on the mathematical part and also the application part contribution to electrical engineering. So this is a very famous professor. I show you, just you can visit this website of Duke. Go to Duke, go to ECE, you can see this. This is a great professor you want respect and advise your kids to follow this example if you truly like STEM. So I haven't done that to my kids yet. So let's go back to this. So we look at the results using a neural fuzzy. And then what do? You train data versus test data, and then see how that works. See that the training data, and after it's trained, this error is at this level, and the new group of test data, this error is like this. So, and the same thing for predicting, say, this using D3 and F5, and this one uses D2 and D5. So and actually this is just show how wavelet transform help us generate the precision details means, and then form the feature vector, and to use that vector we're going to use three different methods for classification or for detection. Detection means normal versus fault. Classification means you classify between normal fault 1 and fault 2 and fault 3. So and then as here we mentioned that somewhere because to do further analysis, the group did more tests. It designed a force, create a force on the bearing, rolling elements, the inner rest, outer rest, with smaller scale force defects means 7 mil, 14 mils, and 21 mils. So previously that's 40 mils. We just want to test the method. So we create a big level defects. And now we reduce that to 21, 14, and 7. So so this is much smaller than 4 mils. What we want to do is we want to see how we can develop methods for early detection and diagnosis. Eventually, we use that for even online prognosis. So as early detection and prognosis, prognosis means you can predict the evolution of the force. I mean, that part may need the model for evolution. That's different part. But early detection would make the prognosis possible by using the first principle for evolution model. So that's the part. That's this part only we only summarize in this conclusion. So, but if you look at my thesis, so this for section host section 44 is talk about how we use this method for Wavelet transform to do for severity study. I'm monitoring basically. Here we mentioned that we use as in the paper we use 7, 14, and 20 mils level different levels of force, and we generate different these different levels force. Now we have 4 groups: 7, 14, 21, and 40 mils, and what we do is in this case we try we try different wavelet bases. Like WT is wavelet basis function. So D1, WT is 1, WT is 2, D3, D4, D9, D10. We try different things, and so no this is details. Sorry. This is details because in this case we use WH 10. We use DB10, but we with DB10 we use level 10 table 10 decomposition. So we have an approximation at 10 and 10 levels details D1 to D10. So by looking at the we have the plot here. So and we put normal 7, 14, 20, and 40. You see, so that we can see the, I mean, obviously you can see the scale, the signal as the forward in normal versus 7, this is increased. And then it become noisy increase. And this one you cannot really tell. And this one, yeah, 40, the signal scale is larger than the previous one. But it's, can you just define a threshold? Nah, it's because it's noisy. It's not so reliable to just use threshold to tell this. So when you decompose that, you become better. You got a better chance to detect that, but not for all the force. Like here, you can easily detect. So here, 2140 is not easy to detect, but this one give you tell you the difference between this. But yeah, and the approximation goes that way. So this is preliminary study, and we did not really draw a full conclusion at this point. And what can we? How can we really use? Can we use the vector that contains uh, D1 to D10 and approximation signal, and using neural fuzzy to train it and classify it. I believe you can do so because that's the power of neural network and the machine learning. So you can definitely do that. But can you really generalize that and provide reliable classification and detection? We haven't done that in it's a potential study because that at that time we did not really have time to do all this and we need to collect more test data for testing. But this part really produced the idea for moving from this is really from normal to a big four, and then we look at the potential method for detection. Yeah, can you detect that when is detect means separate between normal and for conditions, whether it's a 7, 14, 21, or 40. And now we have D1 and the D9 and D10 and 1 can really help you separate that. And severity monitoring can D1 and D2 can help you monitor that and approximation. So abrupt changes, that means there's a big changes. Can you check that? So this one can help you detect abrupt changes. So and this is interesting. So then you're gonna you probably will laugh. So if you do all the decomposition, you can really tell the difference. But simply look at the scale of the signal, you can tell. And then why do you do the decomposition? I mean, it's really to the detection and diagnosis need to be very reliable to avoid the false alarms or I mean, it's because with the noise you cannot simply use the threshold to estimate the four. So, but it's still one way. So if you look at the standard deviation, the standard deviation, it's a statistical examination can give you this idea. So I can say for these five different groups that I said, if you do statistics analysis, the mean value looks the same because we already normalized that. But if you do standard deviation, these obviously you can tell the difference between normal 7, 14, 21, and 40. That's statistics calculation really provide the features you need. We call statistics features versus the features you generate from Wavelet transform. So maybe you can even combine them and feed that into MFIS or machine learning classifier. So that's the method proposed in this part of the thesis. So if you have interest, you can do that. Not necessarily using bearing test signal. You can use like medical signals, use flame signals in an engine or anything. So you can use image if you want. You can use Wavelet process image, but it's a 2D signal. It's how you do feature correction. That's a different story. So, but in general, what you can do is the Wavelet really like a microscope. You can decompose the signal and it give you insight of the features of signal at different spectral band. And then if you form the feature vector, then you can classify using either simple method using Euclidean methods, statistic correlation analysis, or correlation coefficient calculation, or using a more complicated method using MFIS, fuzzy neural network, or using something if you want to classify using SOMM, self-organized the map. So to separate clusters. So this really provide a lot of possibilities. And as today in also in today's world is different than 10 years ago. This is really done over 20 years ago. So today I just finished a project with GE Research with DOE funding. We use learning or deep learning. I mean, deep learning basically provide a lot of more powerful tool. So you can fit in time series and help you extract that. But if you can, but still, if you can do transform, value transform, have you extract the features, and the learning will be more effective and more reliable. So this is something I want to share with you. And if you want, look at the paper again, and you have a question you want to send to me. So you can leave comments in the comments area. And also, if you look at thesis, that's my thesis is this for detection and diagnosis of auroral element variance. And my advisor, Candice Loparo, this system control engineering as one of the 4 programs at that time under Department of Electrical Engineering Computer Science. It's Cass Western Reserve, so August 2000. So, and I guess find time to explain more to you about the other part of this thesis in another video. Talk with you later. Talk with you later. Thank you for watching this video. If you like to watch more, you can click like and subscribe. Thank you.